Hello everyone, my name is Debanjan Goswami. I'm a fourth year computer science PhD student at Florida State University. The title of my paper is Active Batch Sampling for Multi-Level Classification with Binary User Feedback. The authors are me, Debanjan Goswami, and Shayok Chakraborty. This is presented by me, Debanjan Goswami. Let's talk about the outline of this presentation. We'll start with introduction to active learning, then proposed methodology, then experiment setup, baselines, results, and at the end conclusion of future work. So here's a classical active learning loop where a machine learning model gets trained on a labeled dataset. A few samples are queried to the oracle. The oracle relabels those samples. These are unlabeled samples. Once it gets relabeled, it's get added back to the labeled dataset. The machine learning model gets retrained on the labeled dataset, and that's how our active learning loop works. So in active learning, any machine learning model requires a lot of labeled data to train on. Real world labeled data is very hard to find. There's a huge importance of human expert to label. They're even harder to find. And experts labeling skills has a human factor. They're not error-free. Multi-level learning. A typical deep learning model learns multiple labels assigned to each data of instances present in the training set. Here in this image, we can see that there is a dog and a bird. So that's basically an example of multi-level classification. So we'll talk about our proposed method. It's called active multi-level sampling. So we propose this method. There are a few terms in this method. So we'll first get started with class present uncertainty computations. Then we have label correlation computations, and we also consider the image redundancy in our method. So let's talk about the class presence uncertainty. So basically using the Shannon's entropy to compute the prediction uncertainty of the presence of label yj in image xi, which is represented by hij. Here p is the probability of presence of certain labels for a particular image. Then we have the image redundancy. We use the cosine similarity to quantify the redundancy between a pair of samples where native values are replaced with 0 so that the redundancy of matrix R only contains non-negative entries. As you can see, it is represented by Rij, which is max of 0 or the cosine function. So we'll talk about a little more about the proposed method. Overall, the image and label selection are posed as a constraint optimization problem, and linear programming relaxation is derived to solve the same. A binary matrix Q is defined as each row corresponds to an unlabeled image and each column to a label. In Q, the position of value 1 denotes the image label pairs need to be queried in an ALI iteration. That is, Q is basically our solution matrix. The objective function is defined by the minimum of TRQC plus lambda transpose W W. W is basically defined as a binary vector where Wi equals to 1, which denotes that the image xi is selected for annotation, and for I equals to 0 means it is not selected for annotation. In the objective function, the first term, that is TRQC, denotes that the deep model has low confidence in predicting the presence of the selected labels in corresponding selected images. And the selected labels are highly correlated with other labels of the selected images. Whereas in the second term, we basically ensures that the selected images have the minimum redundancy among them. So we'll talk a little further on this as well. So here we can see these are the few constraints that's associated with the method. So here, E is a matrix of size n cross y. N is the number of samples present, and y is the number of labels with all 1 entries. The small e is a vector size of y cross 1 with all 1 entries, and k is the labeling budget. This is the inner product operator. Tr denotes the trace of a matrix, and y is the number of labels present in the dataset. So we'll talk about the first constraint, which denotes the number of queries present by Q is equal to the specified budget K. The second constraint ensures that the number of ones in each row of Q is less than or equal to Ymax. Ymax is the specified limit for the number of samples, that's a number of labels that can be queried for a particular image of sample. The third constraint denotes that Wi is equal to 1 if there is at least one entry with value 1 of q, and Wi is equal to 0 if all entries in row I of q have value 0. The fourth constraint denotes here that W is a binary vector and Q is a binary matrix. So we use three challenging datasets in our experiments. The first one is NUS-wide. The NUS-wide dataset contains a lot of images with a lot of tags. MIML is also very famous, and COCO is one of the most recognized datasets with 123K images of 80 object categories. So we'll talk about how data split for active learning works. So each dataset has been split into three parts: the train, unlabeled, and test. These are the details of the training and unlabeled and test set for all three datasets that we used in our experiments. The multi-level learner model. So we used ResNext 50 deep model pre-trained on the ImageNet 1K dataset as the underlying convolution CNN network. The input images are scaled and normalized to a fixed size of 256 cross 256 pixels and fed into the CNN. And these are some of the hyperparameters we use in the experiment: learning rate of 0.001, that says of 32. Then we'll talk about some active learning parameters as well. The query budget K has been taken as 200 for NUS-wide and 40 for MIML and 60 for COCO dataset. The parameters lambda, Ymax, alpha, beta were taken as these values respectively, and about 25 IL iterations, that is active learning iterations, are performed to study the performance of the proposed algorithm. Here are some of the baselines used: the quered, OD, LML, and CMAL. Quered is basically a min-max L strategy that combined informativeness and representativeness for active selection. OD exploited the both uncertainty and diversity in the instance space, as well as label space and active query space. LML trains a low-rank mapping matrix to identify the relation between the feature space and the label space of a certain multi-level dataset, and uses uncertainty sampling to query the informative pairs. CMAL queries the most informative example level pairs by leveraging uncertainty, level correlation, and level space sparsity, and then queries the most probable positive pairs of the selected pair in a multi-instance learning setup. These are four baselines that we used to compare our proposed algorithm. So here are the active learning results for NUS-wide, MIML, and COCO. As you can see, the proposed method, we have in the y-axis the F1 score, and in x-axis with the iteration number. As you can see, the black one, which is the proposed method, actually outperformed all other baselines present here. For NUS-wide, MIML, it has been pretty consistent, especially from 15 to 25. You can see for these iterations, the performance has been topped. And for COCO, we also see a pretty consistent result from our proposed method. We'll talk about the query budget of the size experiment results. So for budget 100, we can see our proposed method have performed very well. And for 200, it's slightly not at par with the budget 100, but still perform consistently. For 300, it's a good performance. And for budget 400, still a pretty good performance, as you can see, compared to our other baselines here. So we also studied the backbone architecture models. Here we use the VGG16 model and the Inception V3 model as well. So in this experiments, we also see that those, however, those baselines have performed well, but our method, our proposed method, have been pretty consistent, especially in the last 10 iterations, irrespective of all the experiments here. So this is a very common scenario where these 10 iterations, our proposed method have kind of outperformed all the baselines in every possible way. Here's a short conclusion and future work that we have you have in mind. In this paper, we propose a novel batch mode active learning framework for multi-level learning. We posed the image level pair selection as a binary integer programming problem and derived a linear programming relaxation to identify images and corresponding labels. As part of the future work, we plan to study the performance of our framework on other multi-level learning applications, such as text mining and bioinformatics, etc. Thank you for listening to my presentation.